Okay, in this one we have a Venturi tube and it has water flowing in it. And the Venturi tube in this problem has mercury as the indicator, and it shows a height difference. It gives you the value, and then it also gives you dimensions of the sections of the Venturi tube. So let's go ahead and take a look at the sketch of this situation. Okay, so here it is. We have this tube with 45 centimeter diameter here and a 15 centimeter diameter in the constricted part. And what we see is that the mercury has 37.5 centimeters higher here, which we know then that this is a lower pressure than this area right here by the mercury. But of course you know that this Venturi tube, the way it works is in a consistent or steady state condition of flow, the velocity times the area of this section must equal the velocity times the area of this section. So this has a faster velocity. And you know that the higher dynamic velocity means the hydrostatic pressure will drop in this area compared to this one here. So we're going to use our Bernoulli equation to solve this. And let's go ahead and get a clean sheet here. Let's see, how am I going to do that? So the Bernoulli equation we know is, in this case, since our situation has no altitude change, so this is all the same z dimension here, our equation is going to be pressure, let me put points 1, points 2, pressure at point 1 plus rho over 2 v1 squared equals pressure at point 2 plus rho over 2 v2 squared. Now I can rearrange this to tell me that the pressure difference, so P2 minus P1, is equal to rho over 2 v1 squared minus v2 squared. And we know that this pressure difference is given by, going back in the slide, is given by this difference in pressure on the Venturi tube here. So we know that is equal to rho of the mercury times gravity times the height of that mercury. So let's go ahead and compute that pressure. We know it's 13.6 times the density of water, 1,000 kilograms per meter cubed, times gravity, which is 9.8 meters per second squared, times 37 centimeters, which is 0.375 meters. So in doing that math, we see that we've got meters squared on the top and meters on the bottom. Or another way of saying that is kilogram meters per second squared. There's a Newton here per meter squared. Newton per meter squared, or Pascal. So we've got that the pressure is, now let's kind of do the numbers. We know the pressure is in pascals, or Newton per meter squared. We've got roughly 13,000 or 14,000 times 10 is 140,000. And about a little over a third of that is, what is that? 140,000, so a little bit of 40, there's going to be something around 45,000 pascals. So if we use a computer to do this, what do we get? Differential pressure here. So this is equal to 4,980. And when we solve here for the velocity, we get v1 squared minus v2 squared is equal to 2 times 4,980 divided by the density, 1,000 kilograms per, this is newtons per meter squared, kilograms per meter cubed. We know then that this is equal to this is equal to, let's see, 50,000. I'm going to go 1, 2, 3, 2, 3. So it's about 50 times 2 is about 100. About 100 meters squared per second squared is v1 squared minus v2 squared. Okay, we're getting closer, but we've got a couple of unknowns here. And so we're going to have to call on another equation, probably the continuity equation. We know that the area times v1 squared equals the area 2 times v2 squared. No, not squared. It's area 1 times v1 is area 2 times v2. So we know that in terms of the area, we know the area, presuming it's the cross section is a circle, we know the area is equal to pi over 4 times the diameter squared. So we know the pi over 4 terms are going to drop out when we stick them in here. So we know here that the area area 1 is equal to d2 squared over d1 squared times v2. Now, another way of saying that is the ratio d2 over d1, that thing squared times v2 is v1. You can see I'm getting a little bit messy here. Let me go to the next slide. So v2 is, no, excuse me, v1 is d2 d1 squared times v2. And we know that d2 is 15 millimeters. d1 is 45 millimeters. When I square this, I know that I just get 1/9, because 15 is a third of 45, so 1/9 times v2 is v1. There's definitely something wrong with that. Well, no, okay, so v1 is 1/10 of v2. v1 I'm expecting to be slower because v1 is much larger in cross-sectional area than v2. Okay, I'm okay with that. So we've got v1 being, v1 is 1/9 v2, and if we go back to our previous slide, we can plug in those relationships. v1 is 1/9 v2. Let's take these numbers here and work with them. So let's go v1 squared minus v2 squared is equal to 100 meters squared per second squared, which is equal to v1 is 1/9 squared v2 squared minus v2 squared is 100. This ends up, nope, I'm going to carry my units through because they're going to save me in the end. Meters squared per second squared is going to be, I'm going to take v2 squared. I looks like I'm going to get a negative number. And I do think I'm going to get a negative number. And I'm looking back on this, and I see that here's 0.2, here's 0.1. P2 minus P1, we know pressure 2 is lower than pressure 1. So we know this is, in fact, going to be a negative number, P2 minus P1. So I'm going to make that a negative number. I put this positive number here because I computed it from this set of numbers over here, but in reality I know that this pressure is lower. So I'm going to go back to my equations and turn this number right here into a negative number to make myself happy. I don't like randomly doing that, but this is now going to be a negative number here. negative. So now I have 1/9 squared minus 1 is equal to that, and I'm going to solve for V2. I'm not going to do that in my head. V2, I'm going to use a calculator. V2 is 10.1. Therefore, V1 is 1/9 that. So V1 is 1/9 this. It turns out is 1.1 meters per second. Okay, I think that's what we were looking for, those two velocities.